So, good morning, everyone. So, today is the second lecture on the topic of approximate inference. This is chapter 19 of the deep learning course. And if you recall, this is the last part of our deep learning textbook. And this part is part number 3. It deals with research in deep learning. So the topics are a bit advanced. And we are at the last but one chapter, which kind of takes us to one of the more advanced topics. I feel it's an important topic to be familiar with, particularly if you're interested in research in deep learning, how you could contribute. So again, what is chapter 19? The title is Approximate Inference. We started it at the last lecture. We're kind of midway through the chapter, but I think it's necessary to refresh your memory as to what is approximate inference about. Again, let us refresh our memory about what is machine learning about. Machine learning has two components. One is the learning part, the other one is the inference part. Learning part is to figure out all the parameters of the network, and inference is to use the learned model to infer as to what is to be associated with an input. So if it is a pure generative model using unsupervised learning, a goal would be to something like generate the probability of this input. I present a visible input and say, what is the probability of this according to the model that you have? And why would we want to calculate the probability of something? It is so that you can use it in learning, for example. So the inference part, although we said it's different from the learning part, the inference part is needed for the learning part. And so the learning part would want to take an input and say, what is the probability associated with it? And we like to increase the parameters of the network. Those are all the weights in the network to increase the probability. That's what's called maximum likelihood. If we have a whole set of inputs, we want to increase the probability of all of these inputs together, the sum of all of them, sum of all the log probabilities, I should say. And we would like the parameters to be chosen like that. So that is maximum likelihood learning. And maximum likelihood learning requires inference. So inference is when I give you an input to calculate the probability. That is the inference problem. And that inference problem is intractable because of the structure of the network. If it is very deep, the number of possible combinations of connections, values that the nodes can take can be high, in which case it's an impossible computation to do inference. So we resort to approximate inference. So that is the motivation for approximate inference. And what are the kinds of approximate inference methods that exist? These approximate inference methods largely deal with replacing the distribution P that is modeling the data by a Q. So we say, let us not work with the real P. It is too complicated. The network has modeled it. It is too complicated for us to deal with. So rather than calculating the probability with the real thing, we'll use an approximation called a Q. So then we have to decide, how do you get that Q? So this now becomes an optimization problem, saying we would like to find a Q that in some sense best approximates P. And if this Q that we have chosen is straightforward, we can use that Q to do inference, assuming it's a fairly simple probability distribution, and inference is not a computationally difficult problem with Q. So the entire problem of approximate inference, the central problem, I should say, becomes that of approximating, or becomes an optimization problem of finding the appropriate Q. Okay, so that's what we did last time, basically to show how approximate inference is stated as approximate optimization, right? So what we have to then ask is, what are the methods for doing this optimization? And there are several methods. As in many other topics in machine learning, deep learning, we study some simple methods. You don't want to be asking, give me something very fancy and so that I'll use it. What should I be using today? Okay, that comes a little bit later if you're a student of deep learning. Uh, and we want to learn the concepts here. And then we say, well, that's what's going to be used. So the first method we look at is based on a classic method of machine learning called expectation maximization, or EM. You probably had a course on introductory machine learning and encountered what is EM. Oh, no harm in visiting it again. It's an important concept. It keeps appearing again and again. So we'll look at that part. And why does EM come into play here? Keep in mind that EM is a method for maximum likelihood estimation of parameters. When some of the variables are unknown, when you have latent variables, you use EM. A famous example of using EM is in mixture models, Gaussian mixture models, where we assume that the probability distribution consists of K Gaussians, right? Multimodal Gaussians. And we have the observed data, but we don't know the means of each of these Gaussians and the variances of each of these Gaussians and the priors of each of these Gaussians. Those all have to be learned from the data. And expectation maximization is a classic method to find those kinds of parameters of a Gaussian mixture model. Of course, there are some simple methods for doing Gaussian mixture model, like k-means clustering does the same thing, but it's an approximate method. It doesn't give you variances and priors and things like that. So it gives you the means though. So expectation maximization is a famous method. And why does expectation maximization play a role in deep learning? Is we want that Q. So we argue here that Q is an unknown, it's a latent variable, and we would like to determine that Q. And when we have observed all these values of the input are the visible nodes V. In these networks, we use the symbol V to indicate all the visible nodes. It's coming from the computer vision community, where we have a camera picture, the visible nodes. We don't know the latent variables, which are the hidden nodes. And so we have this framework and we need to figure out Q. So the first method we use is expectation maximization, which gives you some insights into how this approximate inference can be done. So this requires a little bit of rigor in your thinking. What exactly is happening? It's a sequence of things to understand approximate inference. We begin with we need inference for learning, and then we say that it is hard, and we replace inference by optimization. And in optimization, the method we use is all methods of optimization are approximate methods. And then we say, well, we could use expectation maximization for that, solving that problem. Okay, that will be the first method we look at. The second method of approximate inference we look at is called MAP, or maximum a posteriori probability inference. So this says rather than constructing a distribution of H given V is observed, right? That's the data for each data. Instead of calculating P of H given V, we get a point estimate for H. And point estimate, so these are the differences in machine learning, that the answers can be given as point values or can be given as distributions, just like maximum likelihood versus Bayesian approach in machine learning. So the map approach is a point estimate method. It's, even in the classic problem of supervised learning, when I present an image to you, if the output comes out exactly and says that is a 7 that you have presented to me among handwritten digits, that's called a maximum a posteriori probability inference. It's telling you the answer is 7. Whereas a more general inference would not be maximum a posteriori probability inference. It would give you a distribution over all the possible labels, and it would go through 0 through 9 and gives you the probabilities of each of these digits. So map inference is like that. And map inference is useful even in approximate inference in a certain context. So we'll see what that is. So it's not a very general approach. And the third approach is the most famous of the approximate inference methods. It's called variational inference. All right. So that is the more complicated looking one, but there are some simple solutions there again, saying you can find that Q you are looking for to replace your P by a simple distribution of a product of distributions, assuming all these variables are independent. And you can use that called mean field approximation. So we look at that and then a variation of this called arbitrary structured probabilistic graphical models. So we're saying, here is the network. We're going to, first of all, replace it with a very simple thing, multiply all these probabilities with all these variables. That's a simple version. The other one says, replace it with a more complicated distribution with many nodes and many connections. But it need not be as complicated as a network. And we work with this to do some inference. So we look at both of these. So there are half a dozen methods, and variational inference is probably the most useful of these. But we want to learn what the earlier methods are to get a sense of tackling the problem and reintroducing us to many basic concepts. So in terms of the slides for the lecture today, there are going to be three sets. The first set will be on approximate inference using expectation maximization. It's a small number of slides, basically introduces the EM algorithm or expectation maximization algorithm, which basically has two steps. It's an iterative process. There is an E step and an M step and an E step and an M step and an E step and an M step until some convergence criterion is satisfied. EM. That's what EM is. It's the most famous maximum likelihood estimation algorithm. So we're going to visit that in the first set of slides on expectation maximization. And again, the second set is going to be approximate inference using point estimates or maximum a posteriori probability. And the third set is the beginning of approximate inference using variational methods. So let me share the slides right now. I can figure out where the button for sharing is going to be. Okay, here it is. And share. Okay, there we are. So, it is showing an old method here, inferences optimization. I guess I didn't want this particular older set of slides. I wanted, okay, I think this is the one I wanted. Okay, share. Let's try this one. Okay, so yeah, this is what I wanted. I hope you can see it. It's titled Approximate Inference Using Expectation Maximization. Can you see it, Setu? I need to unmute all here for this to work. Okay. Can you see the slides, Setu?
Yes, sir, we can see the slides.
Okay, very good, very good. Okay. All right. I'm going to. Okay, so let's move on here into what we've got. So we are at the bullet point number 2. So we have finished the task of inference. I described it earlier on here, and also talked about intractability of inference. All right, the intractability occurs from the fact that we need to sum over a lot of variables, and to get P of H, from P of H comma V, we need to sum out the variables here of H of V to get P of H. So that is intractable. And inference treated as an optimization problem. I finished that. So we're on to expectation maximization. All right, this is a good diagram to keep in mind of approximate inference. This is not about EM, it's just about the approximate inference problem. So we want to compute log of P of V given a set of parameters. Theta is just the parameters of the network, all the weights in the network. We want to compute the probability of V because we would like to choose these thetas that's going to increase this probability as much as possible. Compute log likelihood of set of values. For every one of the variables, we need to compute the log probability and sum them all up, and we want to increase theta so that that quantity becomes large. So that's what we're after, log P, V, theta. And so that is some quantity, some number, log probability. It's some real number whose value is this entire length here. That's the value of this. We're saying that is a hard quantity, but we are breaking it up into two parts. And one part is referred to as the evidence lower bound, L of V theta Q. And this Q is chosen such that the Kullback-Leibler divergence between Q and P. P is a real distribution. And in this case, it's stated in terms of the conditional distribution. And that is not critical for this definition. It's simple. We can show that mathematically. Why is that H given V? We can prove this part of it. Let's take it that this Q of H given V, the distance between that and P of H given V is as small as possible, ideally equal to 0. In which case, this evidence lower bound L V theta Q is exactly equal to log P. Okay, so this is referred to as KL divergence. We'll see this one more time. And I'll remind you of the derivation that led us to this. But we have something called evidence lower bound. It's fairly easy to compute. L of V theta Q, given a set of parameters, given the set of values for the visible units, and given the function Q, we can compute that easily. That's great. If you can compute that easily, we have figured out this much of this value. The only part that we don't know is the KL divergence part. So now we say the optimization problem is finding the Q such that this quantity is small as possible. So the expectation maximization approach says maximize L. Well, if you maximize L, it will go all the way to the top. Maximize L with respect to Q. Choose the Q carefully such that you are going to maximize it. And the M step says maximize L with respect to theta. So we're going to have, there's a maximization. V, of course, is fixed. It's something given input. Theta and Q are the variables here. So this says there are two steps in this. Each of them keeps the other constant. It says with respect to Q, you increase this. And with respect to theta, you increase this. And hopefully in all of this process, we end up finding a fairly close value here, and L, of course, would become an approximation. This slide, again, some classic figures here of what is expectation maximization. And you can carry away this notion that whatever be the problem you're working with, if it has got unknown values, unknown parameters, then you can regard them as a problem that can be attempted with expectation maximization. And I gave you the example of Gaussian mixture model, where we have the data, but we don't know which subclass they belong to, which Gaussian they belong to, assuming it's a multimodal k-means type of distribution. And so we estimate that using expectation maximization. And the way expectation maximization works is it's got an E step and it's got an M step. In an E step, we guess the missing data. And you can keep in mind the k-means problem. We start with some arbitrary set of k-means in the data space, and so guess it. We take that, could be the starting point. It could be wrong. The guess could be wrong. And we then go and in the M step, we update the parameters saying, okay, those are the parameters, and you've got your data. Now calculate all the parameters and see what should be the parameter value. So what we do in k-means is once we have the k-means assumed, we go and find out as to, we assign to all the variables, their mean, based on being close to it. So that's what the k-means part of it is. And then we estimate the parameters, that is the new means for the classes. So E step is to guess the missing data, and M step is to update the parameters. This is a back and forth process. Unlike other approximate inference algorithms, EM is not approximate inference, but an approach to learning with an approximate posterior. So there is a characterization of it that we are dealing with a distribution that is being updated. So it alternates two steps until convergence. E step is the expectation step, and the M step is the maximization step. It's also shown in terms of a flow chart. We initialize the values, and then we have an expectation step, a maximization step, and we ask the question, is it converged? If it is no, we go back. That is, if there is no change, we go back, and then yeah, in the sense it is, if it is no change, then we stop, otherwise we go back. So that's the general this is a general slide about expectation maximization. But now specifically for approximate inference in deep learning, the E step, or the expectation step, let theta naught denote the value of parameters at the beginning of the step. This is all your weights in your network. And we say, let this Q of hi given V be equal to P of hi given Vi for all indices I of the training example. So this says, we're going to choose the Q to be whatever should be the value of P given that set of parameters. Let's not worry about the interactability of P of H and V at this point. So let us say we set Q to the value that you have. Here is a network. And in this network, when you present V for these thetas, what is the probability associated with each of the components of the H nodes? And that is exactly what Q is going to be. So Q is assigning to all the variables some values, and we are saying set it Q for whatever be the set of parameters you have in the network. And for all indices I of the training examples I, so this is running through all the samples here, training examples, and both batch and mini batch variants are valid. By this we mean Q is defined in terms of the current parameter values of theta. So whatever be the theta naught values, Q is defined by the current parameters theta naught. And note that if we change the value of theta, then the P will change, but Q is has been fixed to be the original value you have. In the M step, we're going to go and change theta and come back. But in the E step, we have Q is being set to whatever be the current value is given by the network. In the M step, we completely or partially maximize. This is the again the elbow. This is the evidence bound that we have, and we have Vi theta Q. We saw this same expression earlier on. Let's remind ourselves. This is evidence lower bound. That's what this is. Okay, so that stands for evidence lower bound. L stands for lower bound. That's what L is. It's not likelihood here. It's lower bound. So the evidence lower bound over all the samples I, training examples I, we are computing the evidence lower bound with respect to theta using your optimization algorithm of choice. So this says you have a fixed value of Q, and what should be the value of the parameters theta given this set of values Vi. And so we look at, I mean, here we have fixed a value, a kind of simple distribution. So what value of the parameters is going to make this quantity as high as possible. And so this can be viewed as coordinate ascent algorithm to maximize L. So this is saying keep on increasing. So we fix the value in the beginning of Q, the previous step, and using that Q, we keep on changing theta until we find a maximum. On step one, we maximize L with respect to Q, and on the other, we maximize L with respect to theta. So that's what's going on here. So although E step involves exact inference, we set Q is equal to P, EM uses approximate inference in some sense. And the M step assumes the same value of Q for all theta and introduces gap between L and the true log PV as the M step moves further away from theta naught using the E step. Fortunately, E step reduces gap to 0 again as we enter. So where is the approximate inference? The first step involved the exact value, right? There's no approximation on the inference, it's asking you to do it. But in the second step, we're saying move theta, move theta. So there is some sense is happening. So it seems like an impractical algorithm because the first step says calculate P. But this gives you some insights. Stochastic gradient ascent, we call SGD as a famous learning algorithm for deep learning. The other variant is stochastic gradient ascent instead of descent. Change the positive to negative, we get the other one. On latent variable models is a special case of EM where the M step consists of taking a single step. So you can, it's interesting that even the problem of stochastic gradient descent can be thought of as EM, where we take a gradient step, in the sense we change the parameters, and in the first step evaluate the loss function, I guess, in the E step. Other variants of the EM algorithm can take much larger steps. And for some model families, the M step can even be performed analytically, jumping all the way to the optimal solution. Right? So this is, again, viewpoints. And so there are two insights due to expectation maximization. So this part on expectation maximization applied to approximate inference is to gain some insights that the first insight due to EM is that of maximum likelihood. In learning, model parameters are updated to improve the likelihood, and missing variables provided by estimated prior distribution. So this says the model, okay, that's all it's saying. The model parameters, the theta are updated to improve the likelihood. This insight is not unique to EM. SGD to maximize log likelihood has the same property. So so that's what we say. We change the parameters to increase the likelihood of observing this data set. So and then we calculate a gradient of that log likelihood. Log likelihood gradient computations require taking expectations with respect to the posterior distribution over the hidden unit. So this is what goes on, standard gradient ascent. And the second insight of EM is that we can continue to use one value of Q even after we have moved to a different value of theta. We said fix the Q, and then we keep on updating theta, and then once that converges, we come back to the new value of Q. So this insight is used throughout machine learning to derive large M updates. And deep learning models are too complex to admit a tractable solution for an optimal large M step update. So the second insight, which is more unique to EM, is rarely used. So that is just what this is useful is when you're trying to solve a problem where you have unknown values. I mean, this could even be a simple problem, like you're trying to do machine learning to do medical diagnosis, and you find several variables are missing. So in the chart of the patient, the variables for temperature or blood pressure or anything else is missing. You don't necessarily say, I can't do anything about it. So these are missing variables. Expectation maximization is a method you can bring into play to estimate those missing values. So whenever you have a problem where there are values that are missing, either because it's missing in the data, I guess one could say even for k-means, it's missing in the data because you have not been told whether the sample belongs to group 1 or group 2 or group 3 in the mixture model that you have. That is missing data, we can argue and say we would like to use expectation maximization, where we make an assumption about that, and then determine as to how good an assumption that was and update the assumption. So this is the first part, and we will now go on to the second part. which is that of map inference. This is another short topic. I think I should make sure I share this. New share. Okay, we are on this topic of approximate inference using MAP. MAP in machine learning stands for maximum a posteriori probability. The key word there is maximum. It is when you have a probability distribution, we would like only one value. Actually, that's the most intuitive way to think about it. When you're driving an autonomous vehicle that is driving, it's taking all the sonar and the lidar and the camera inputs, and it's figuring out whether to turn right or left or accelerate or brake. You want only one value for each of these. And so I would say, okay, how much should I turn right? Okay. The normal way of giving an answer for a neural network would be to give a probability distribution and says, you should turn right to this angle with this probability and another angle with a lower probability and so on. Maximum a posteriori probability simply says, just give me one value, which is the most probable value. So map is a very useful concept to give you one value instead of a whole distribution. A whole distribution is useful to carry on to another stage and so on. So we are into item number 3 here, and topics in approximate inference. It's called map inference and sparse coding. So let's define a map inference mathematically. So the usual form of inference is compute distribution of a set of variables given another. So if we have visible and hidden units in the network, in regular inference, we're interested in saying what is the probability of H given V, right? If it is a supervised learning problem, H may be just classes. What is the probability of each class given the image that you have? But we are stating in terms of a neural network with hidden units, and probably it is even a generative model which has no labeled outputs. So we're interested in P of H given V. So the map inference is to compute H star equal to arg max PHV over all H. What this means is, give me the value of H for which that probability P of H given V is maximum over all possible values of H, and we call that as H star. So that's what maximum a posteriori probability inference is. So why does this appear in approximate inference? So we say map inference is not approximate inference. It does compute the exact most likely value of H star. It just tells you what is the most likely value of the hidden unit or hidden units, right? It could be more than a single value. So we say H is a vector, and what is the most likely value of that vector? And it gives you, map inference gives you that. However, if you wish to develop a learning process based on maximizing LVHQ, remember we are interested in computing this thing called the lower bound, elbow, evidence lower bound. Then it's helpful to think of map inference as a procedure that provides a value of Q. So we're saying, give me a value of Q that corresponds to it. In this sense, map inference is approximate inference. It does not provide the optimal Q, but it just gives you a value of Q. And we'll now talk about restricting the family Q. Recall that exact inference consists of L B theta Q is equal to expected value over all values of H of log P H comma V plus HQ. We derived this quantity. Actually, we didn't define L like this. We defined it in terms of the elbow and the Kullback-Leibler divergence, but a little bit of algebra was needed. And we just brought it to this particular form. It looks like a very strange theorem or something, but it's really derivable by a simple definition what is the value of log PV theta, and that can be written in two parts involving a Kullback-Leibler divergence, and then realizing that Kullback-Leibler divergence involves some integral, and that brings in entropy of Q. So H of Q is the entropy of Q. It's the disorder in the distribution Q here. And so this evidence lower bound has an expectation of log P over the distribution over H, over all possible values of H, the joint distribution here. With respect to Q over an unrestricted probability distributions Q, over all possible Q, using an exact optimization algorithm. So it says, find the Q that maximizes this. We can derive map inference as a form of approximate inference by restricting the family of distributions Q may be drawn from. So this becomes approximate inference when we say we restrict Q. So although we are using exact inference of the parameters, we are allowing only for a restricted set Q. In that sense, it becomes approximate inference. Q as a point estimate. Here's an interesting side issue that is being shown. And supposing Q was not a distribution of any sort, it's a very peculiar distribution which has got a value of infinity at one point and 0 elsewhere, and that is referred to as a Dirac delta distribution, right? Named after Paul Dirac, who was one of the quantum physics people. I think he won the Nobel Prize, right? Actually, I had visited Cambridge University, and there is one building where Isaac Newton, Trinity College is one building. It says, this is where Isaac Newton was in Trinity College at Cambridge. And here is another building. This is where Paul Dirac was. And why that is interesting is Isaac Newton is classical physics, right? And Dirac was all about quantum physics, so different kind of physics. They're opposed to each other. One is about large quantity, large bodies, another one is about small bodies and so on. So anyway, Dirac is a famous guy, but he is known in machine learning not because of all of quantum physics, although there are some quantum physics ideas. Here we're just using a simple probability distribution named after him, which takes a single peak here and says it is infinity at this point and 0 elsewhere. And that integrates to 1, and that overall values. And we say Q of H given me, supposing we take the Q distribution we're interested in as a Dirac delta distribution of H minus Q. So there is some parameter it has. That value of H you're interested in. And then it's a delta function peaking not exactly at H, at a distance from it. So it's delta of H minus mu. This means we can now control Q entirely via mu. Mu is simply this separation of where the peak is occurring for the delta. Dropping terms of L that does not vary with mu, we are left with the optimization problem. Mu star is equal to R max log. So this is simplifying it for the Dirac delta problem, which is equivalent to the map inference problem, H star. So this becomes a special problem. And we can use learning similar to EM, alternate between inferring H star and then updating theta. So there is an EM-like algorithm for this. When we studied EM just earlier on, we said EM is not very practical. But then we look at this very peculiar case of a Q distribution that is a Dirac delta. EM seems to be useful here. So that's why it was useful to have looked at EM first. Map inference is actually used. Map inference is commonly used in deep learning as a feature extractor, as which feature should I use, which one feature should I use, or which subset should I use and not others, and as a learning mechanism, primarily used for what are called sparse coding models, which we see again in the variational methods. Sparse coding is a particular model the linear factor model, it imposes a sparsity inducing prior on hidden units. And it's being defined here. P of HI has got this form, and then we have a linear transformation and noise type of thing coming into play. Even in this model, representing P of H given V is difficult because the network involves a massive clique and so on. So inference here is hard. Well, inference is hard throughout deep learning. And they're saying it's hard even for some simple model like sparse coding, and map solution could be used here. Okay, that's part number 2. So we haven't really studied very practical things. We just talked about EM as a methodology that could be used to come up with a Q in the optimization problem. Or we could use map solution in very peculiar cases like direct delta model and so on. Just introduce some of these concepts. One has to have this repertoire to go on to, all right. So I need to do a new share now. And I guess I need to open the last one. So this is variational inference is what I'm looking for in my set of slides. Okay, there we are. There we are. And we are on to this topic of variational inference and learning. Okay, so we're on to the main meat of this approximate inference methods. I hope you can still see that.
Yes, sir.
Okay, very good.
You are seeing it.
Yeah,
Yes, sir.
thank you very much. Okay, so we are into this
No problem.
third part of our lecture today. It is titled Variational Inference and Learning. Okay, again, a topic you keep coming across in machine learning, deep learning quite a bit. So no harm. So we can look at it in different ways. So today we are looking at it from the deep learning viewpoint. And again, where we are is it is the topic labeled 4, Variational Inference and Learning. We just finished expectation maximization. We finished map inference, and we are on to variational inference and learning. So again, every time I start one of these subtopics, I remind you where we are, because very easy to get lost saying, okay, what are we trying to do? I don't even know where we are beginning. Okay, so let's try once again. What is the setup for variational inference? So I'm again trying to convey to you the problem that we are looking at. So we have some network here with hidden units here. V is the visible units, and there are some connections in between all of these. It need not be an RBM. It could be a very complicated set of H here, but we simply denote it by V and H. Observed variables are V, and the latent variables are H. And we have a joint distribution P of V comma H. Theta is a set of parameters. Once you have a set of parameters, and we can assign a probability to any value of V, any value of H, since we know the weights there. Theta is what makes it possible to do that. It is a Gibbs distribution that describes, once you know all the connections, that is exactly defined by a Gibbs distribution, which means we know the probability distribution. Of course, parameter Z plays a role inside the distribution. Okay, so anyway, that's the distribution. And we're saying we'd like to compute log PV of theta. So let's say we just want to compute this. I give you a set of values, and then I want to calculate the probability associated with this input. And why are we interested in doing that? So as to choose theta to increase it. So we're saying when we present it here, we would like this model to give that as high a probability as possible, And that can only be done by changing its value of theta, which are all the weights here. And why are we doing that is for a large number of visible units. The examples that we have presented to the network, we'd like to maximize the probability associated to all the data. And we want this theta to be fixed such that it does that. So this we refer to as a maximum likelihood estimation of the parameters of the distribution for your data. All right, now so anyway, wherever we are saying we would like to calculate that PV of theta, wherever we are missing terms of theta. And that PV of theta is given by marginalizing over the joint distribution. So we are summing out the variable edge. So this is the sum rule of probability. When you want the marginal V, we sum out the variable edge, and that is how we get the marginal from the joint of PV edge. And we're saying we know the joint, right? So we know PV edge because the model for any given set of values gives you a value of the probability for all these combination of values. We just need to sum it out for all values of edge. But it is too costly to marginalize edge because the number of possible values that edge can take is impossibly large, because you can have a large number of hidden units, and the number of values, combinations of values that they can take can be enormous. Even if each unit takes only 2 values, there are n hidden units. There are 2 to the power of n values. And even for a small network with 100 units, 2 to the power of 100 values. It's impossibly large number. So it's not possible to compute this summation over all possible values of edge. So we're saying instead of computing this PV theta, compute a lower bound LV theta Q on PV theta. So that's where this whole thing about the elbow comes into play. So log PV theta is the value given between the 2 gray lines here. And we are saying, let us compute this evidence lower bound, which is this line. And it's not anything magical at all. This evidence lower bound is defined right here, is equal to log PV theta. That's exactly what you're looking for, minus the Kullback-Leibler divergence between a Q distribution and a P distribution, defined in terms of conditionals here. And if this, if we have chosen the Q of H given V nicely, then DKL goes away and your L becomes exactly equal to log. So this line here reaches all the way to the top. So we can say that the evidence lower bound is exactly equal to the log probability. In general, we have now this expression here, we did algebra and said that is exactly the same as this expression. So this, note that this equation for L V theta Q different from this equation for L V theta Q. In this case, it was in terms of log PV theta, which we know what it says, and we know the DKL. Here, there's no, the right-hand side looks quite different. The expected value of H given Q log PHV, that is the joint distribution, which comes out of this. Take the log probability and expected value over all possible values of H taken from this Q distribution that we are defining. In the sense, you know, Q is something is up to you to define. So one can take all the values. And then this is the entropy of the Q distribution. So this formula has become this formula. Which this one looks like, how did you get that? So we can get it from here. We can just by doing algebra. And so this is what is going on. This is a setup for variational inference. And now the methods for approximate inference, some we already seen, and now we're going to see some more. First of all, this first bullet point is simply saying evidence lower bound is a lower bound on log PV theta, which we just saw in the last slide. And inference is viewed as maximizing L with respect to Q. That's what we said. Find a Q such that L is maximized. And the learning problem is maximizing L with respect to theta. So learning and inference go together here is to find the parameters theta that are going to maximize L. So there are 2 parameters involved here, V and this is theta and Q. So maximizing this is done in parts. EM allows large learning steps with a fixed Q. We saw that. And then learning based on map inference, learn using a point estimate of PHV rather than inferring entire distribution. And the next one is more general approach to variational inference. So variational learning and inference. So we go to these more general approaches. So what are some common variational approaches? Somebody says, I'm using a variational approach to learning with my network. And that would involve choosing some Q that you use in order to estimate probabilities and to change the values of theta and so on, the weights. The mean field approach is again coming from physics. You know, the term, where you would get this word mean field, you know, something to do with the electromagnetic field in statistical physics. They say Q is a factorial distribution. It says QHV consists of QHI given V. This is not our samples, unfortunately. The symbol subscript is I is not samples here over all the elements of the vector H. So it says they're all independent for a given V. So it's a simple approach. And so this gives you a sense. Supposing we had a complicated probabilistic graphical model with many variables, many connections, and this is how the correlations all exist in this world. Supposing we say, oh, I'm going to throw out all the connections you've given me, I'll replace it by simply assuming every node is independent. No connections in this network. So only nodes, no lines, no edges. What you're basically saying is they're all independent variables. There is no dependency between these variables. So the joint probability for all the variables is simply the product of all the probabilities. So that is the essence of a mean field approach, that you're assuming some severe independence here. All of these hidden units, they don't have anything to do with each other. But anyway, it's an approximate approach. Structured variational approach says impose any PGM on Q. It says, don't assume they're all independent. Whatever combination you want to have on it, it's still tractable, you can use. So those are the two approaches. There is still more stuff here about the variational approach here. Why the word variational? Specifying how to factorize. In the discrete case, optimize finite number of variables describing Q distribution. We have the discrete case, and supposing we want to factorize into a product of continuous case, use calculus of variations over a space of functions, and where we determine which function should be used to represent Q. So this brings in that you want that Q using calculus of variations. And why is that coming into play? This is saying Q is a function, and it says of all the possible functions you can have, find the best possible function. So it is very similar to the regular calculus, where we're saying what is the value of the input at which the function is maximum, right? And maxima, minima, that's what we do. Here we're saying, no, we've got a function of some variable, and of all the functions, which function has the highest value, let's say at this point. So that is choosing the functions, and it is called as calculus of variations. Calculus variation is powerful, only need specify factorization, not design of Q. So one more point that is being made here about Kullback-Leibler divergence. Maximizing L means fitting Q to P. So in a sense, when I say I'd like to find a Q, maximizing L with respect to Q is equivalent to minimizing DKL, QH given V, and PH given V. So that's how we defined L anyhow. So this says one appears on the right-hand side of L, and we want that negative quantity to be as small as possible. That will maximize L. In this sense, we are fitting Q to P. It says P is there when we are trying to minimize this DKL. We are trying to find a Q. We are trying to fit the Q to P. Seems like the obvious thing. We got the P and we're going to fit the Q to it. However, we are doing so with the opposite direction of KL divergence than we are used to using for fitting an approximation. When we use maximum likelihood learning to fit a model to data, we minimize DKLP data given model. So it says, well, think about any general problem in machine learning. We've got a distribution of the data and we are trying to make a model for it. And normally we're trying to fit the model to the data. And now here we are going, saying we are trying to fit a Q to the model, right? So it's going in the opposite direction than the usual way of what machine learning or data modeling is all about, right? We're fitting the distribution of the model to the data. Here we are finding a Q to the model. Optimization matches low probabilities. Maximum likelihood encourages model to have high probability where data has high probability. If the data has high probability, saying, hey, these are all clustering, then the model should have high probability there. Optimization based inference encourages Q to have low probability wherever true posterior has low probability. So we have to take it that maximum likelihood, wherever the data has a high probability, give it a high. What about wherever the data has low probability? Optimization says you have to give the model a low probability of that. So we have got two parts to it. So it brings in a little bit more color to Kullback-Leibler divergence. So we wish to approximate P with Q. We have a choice of using DKLPQ or DKLQP. Okay, DKLPQ and DKLQP are not one and the same. So let's say we had a bimodal Gaussian for P and a Gaussian for Q. So we have bimodal Gaussian for P, and then we're trying to fit it with a Q. So we have this dotted line Q over here. And then we have, this was using DKLPQ. So to augment, to minimize that, it's going to find you this particular dotted line. So it's the best possible Gaussian for this bimodal Gaussian. But if you chose Q given P, it's going to find this Gaussian instead of the other one. So that's a very interesting concept, that just because you're using Kullback-Leibler divergence doesn't mean you're going to unique solution. Depends on whether are you fitting the model to the data or the data to the model, and you might get different answers based on the scale divergence here. So the choice of scale divergence, they have different properties as we just saw. And the choice depends on application. And the inference for inference optimization, use Q to P for computational reasons. So some of it is driven not by quality of the results, but computationally fitting Q to P is easier, and the opposite is more expensive. So now that we are established in variational inference, we are trying to find either mean field inference or an arbitrary probabilistic graphical model. We can now look at some more topics: discrete latent variables, calculus of variations, continuous latent variables, and interactions between learning and inference. And how does calculus of variations work? I believe the credit for calculus of variations goes to Lagrange. Right? Credit for calculus goes to Newton. Okay? Newton invented plain calculus, where we are doing maxima of minima of a function, that is ordinary calculus. Calculus of variations is finding which function will be will have a maximum value, right? Again, example of a functional. So we're dealing with functionals. So a function of a function f is known as a functional. So it takes a function as input, gives a value. So we get a single value out of the function. Again, an example of a functional is entropy. So if I give you a probability distribution f over some variable, I can plug in that f into this thing called a functional, and it says, well, for that particular function you gave me, the entropy is 1/2, or the entropy is 1, or entropy is 0.75, or something like that. And you have so we have entropy is a functional. It is a value associated with the function. So then the question comes in: which function is going to make my j functional value the highest? For entropy, if all values are equal in your function, then entropy is maximum. We know that, right? So most uncertainty, when all possible values are equally likely, entropy is the highest. So we can take functional derivatives with respect to individual values of the function f of x at any specific value of x. So we can get a functional derivative with respect to, so the f of x is defined for any specific value. So we can talk about the functional derivative. So is given by the derivative of the functional j, that is the particular function of a function. And we can talk about the derivative of that quantity with respect to a particular function f of x is denoted like this. So this is getting hairy. So functional derivative identity, and for differentiable functions f of x and a differentiable functions g with continuous derivatives, we have an interesting property that g of f and x, so it's a we can write it in this form. And I guess we need these kinds of compositions because this is generally what a deep learning network does. So let's see where this is all going. And so we do some optimization, the function with respect to a vector, and we go on the example of optimizing a functional, and there's a Lagrangian constraint for maximum entropy. So yeah, we bring in Lagrange saying, what are all the constraints you have on this problem? Because we're trying to get a good function, right? That's why we are ending up in calculus of variations here. To find that function, we need all kinds of constraints in the problem to ensure it is, and that Q is going to be a distribution. So to ensure the distribution, the P of x you're working with integrates to 1. And since entropy increases unbounded with variance, we seek distribution with a variance sigma squared. And the problem is underdetermined. I think it's underdetermined rather than undetermined. So we need a Lagrange statement that when we say optimize, we are talking about this Lagrangian of P is minimized, which brings in all these criteria to play. And then we talk about a functional derivative of the Lagrangian. So that is how we end up finding functions and then choosing lambda values. When you have a Lagrangian, we are talking about every constraint has a weight. So that's what we mean by a Lagrangian. And then we're dealing with continuously latent variables here. And so if we restrict our family, QHI for mean field, if we make the mean field approximation, then the optimal QHIV has a form exponential of log PVH. Okay, so it brings it into some simple form of involving the logarithm of the joint probability. Expectation means simply add over all possible values, and that's going to be your Q. Okay, so the whole thing about variational inference boils down very nicely if you are willing to make this mean field approximation, and you get a fairly simple form saying that is how you're going to infer. So you need to figure out the Q model and use that Q model in figuring out the parameters for the learning problem. So that's the kind of conclusion of that story. All right. I'll see if I can give some examples about this next time, as well as the very last part of approximate inference. That will leave us only with chapter 20, which is about generative models, and that will be the last week of classes. Okay. All right. Do you have any questions for me about today's lecture?
Considering the multimodal Gaussian distribution, sir. Hello.
Yes, Shreya, there's a lot of noise. I can
Okay.
yeah.
Multimodal Gaussian distribution. Sir, am I audible?
Okay, maybe I need to mute somebody else. Maybe may not be your microphone. Shreya, try again.
Yes, sir, in the multimodal Gaussian distribution.
Mm-hmm. You said multimodal Gaussian distribution, yes?
Yeah, where you discussed that the expectation maximization.
Now I cannot hear you. The volume is really low. Previously, there was a lot of noise. Now I can't hear you. Okay, go ahead.
Yes, sir, am I audible right now?
Yeah, you are audible, but there is a lot of disturbance. But anyway, you are audible. Yeah.
Okay, sir, in the multimodal Gaussian distribution, we had is like this modes, I mean, from which the data is coming. I mean, what is the probability of each mode? That is the hidden thing, right? That we don't know. I mean, that we try to learn, right?
Okay. In that example, I had multimodal Gaussian. There were two Gaussians there, right? So that slide was just telling you. Supposing I had two distributions, P of Q and P of X and Q of X. Let's say P of X was a multimodal Gaussian, two mode, and Q was a unimodal Gaussian. That slide is
Okay.
simply telling you that if I do Kullback-Leibler divergence of P to Q, you get one answer, and if I do Kullback-Leibler divergence of Q to P, you get a different answer. So in the first answer, we get a very smooth Gaussian over the two peaks, and in the second one, it is simply focusing on one of the two and not the other. So it is saying, watch out. You're going to get different answers whether you are matching P to Q or Q to P. And in this inference problem for deep learning, we are trying to model. We got a model P already there. We got a neural network ready for us. It's a P. So we want a
Okay.
Q that is somehow going to match it. So that is simply saying, if you're going to match Q to P, you're going to get one answer. On the other hand, if you look at it the other way, Q to P, you're going to get another answer. And it says that normally, you're always trying to fit a model to the data. Just think about generally. You have some data and then you want to fit a model to this data. That's what machine learning is about. So you're fitting a model to the data. But here in this approximate inference, we are saying, no, wait a minute. We have a model here already. We are trying to fit a Q to that. It's the opposite direction of fitting. Usual way is P to Q or model to data, but here we are going the other way around. That Q is yet another thing to the model. So that is the only point that was being made, and the point that was also raised here was, isn't that interesting? There is some kind of a relationship between this and Kullback-Leibler divergence of P to Q and Q to P, and it was just an observation. All right. Okay, so that you know what we're trying to do. We are trying to fit a Q to the P. And then multimodal Gaussian was just to explain to you that KL of PQ is different from KL of QP. And it was
Yes.
different answers for that. All right. Look at the slide again carefully to see what is being said. It's just making you understand what is Kullback-Leibler divergence. I think it's worthwhile for you to know what is KL divergence and understand its meaning and implication, because it occurs so often in machine learning. Okay. All right. Good question. Yeah. All right.
And sir, in most of the time, from the data, say I have few models, okay, and I do not know which data I should, I mean, and say I have a data set, and I want to fit each of my model to the data set, but not to the whole data. I know there are some modes, so I will try to find out these are the set of examples it's good for this model one, and that are the another set of examples will be good for model 2. So this is what the key thing is, right? I mean, this is from where these concepts of modes, multi-modes come, right? I mean,
Hmm. Well, you're asking
so
a general question about, I think, expectation maximization or K-mean. Think of K-means. I got all this data that it's got multi. I presume you understand. You know what K-means is very well, right? You know K-means
yes,
clustering, right? Yeah, that's one of
right.
the basic algorithms you learn in pattern recognition. So I got all of this data, and I'd like to model it. There are so many modes in the data, and I am allowed k different modes, and it says what is the best set of modes to model the data, and then but k is fixed, so you keep on changing the data, and you keep on recomputing the means of the clusters until no change occurs. So it says, oh, okay, I fit the data with k-means, and EM basically does the same thing in a more sophisticated way. So it's trying to find how to fit the data. So that is just a general approach. You don't need to get stuck on k-means, or you don't need to get stuck on EM as a solution to multimodal data. EM is a more general technique. Whenever you have something missing, you can try and get those values. It is saying, look at that. In a Gaussian mixture model, there is something missing. What is missing is we don't know which particular mode particular data belongs to, and so that data is missing, and so we can use it for EM can be used for clustering. K-means can be used for clustering, but EM is this powerful method that says whatever be your situation, if there is something missing in your data, I'll show you a clever way of coming up with the answer to that, and we are invoking it here for Q of all things. That's kind of really strange that we're using EM to figure out this Q which we're trying to fit to the P that we are doing. So anyway, that's the role of it. Okay, so think of EM as
Okay.
a very general technique. It's even useful for you when you're missing data. That is a very
Yes.
common practical thing. I don't have all the data. What do I do? One solution is throw away the records where data is missing. And this is saying, okay, wait a minute, that might be valuable data. Hospital records, but every record has something missing in it, right? So you don't want to be throwing out all the records because you're doing a project on machine learning here. So you can use EM to find an answer to all the missing data, and then proceed to what you want to do. So EM is that is why EM is considered to be one of the most important machine learning algorithms. I guess the other important one is backpropagation. Backpropagation is probably number one in terms of its importance, which is stochastic gradient descent, basically. And if you ask which other algorithm is very, very important, it's probably EM. And we keep on bringing it up in various contexts, right? Maybe you can decide which is the third most important algorithm in machine learning that one should know, right? So there are so many. We have already covered so many this semester itself. Maybe you can say k-means, or that's just a version of EM. So it encompasses a lot, and on. Okay, so you can use your imagination as to what it might be, the third most important one. Okay, any other question? All right, I'm going to turn off the recording and the sharing. I'll still stay online in case you want to ask questions about the wrapping up of the semester. So I'm going to stop sharing, and I'm going to stop the